Hi everyone, I will be presenting a deep dive into our GraphQL Federation Gateway. I'm Benjamin Rabier, I work at Grafbase. I will first talk a bit about the challenges of making GraphQL Federation Gateway, what are the different difficulties, the query planning, how we plan the different query, and how we execute it. So let's start with the challenges. We'll start with a very simple query, retrieving a list of feeds. It has a created that. It can be a post of video, retrieve title, and typical GraphQL server. It's pretty trivial, like retrieve a feed, reiterate over different feeds, created that, the title if it's post of video. Now, our service has grown exponentially. We split into 3 different services, feed, post, and video. And we have GraphQL Federation to keep a single unified API. And we already start with our first problem is how do we know which post video to retrieve? Previously, we just knew how to identify them, what to retrieve, and this needs to be explicit in GraphQL Federation. So this is why we have a key directive with field to say that, okay, this is an entity. There's a field name ID that uniquely identifies this particular entity. And for Apollo Federation, there's an entities field where we can retrieve it. There's lookup for composite schemas. First challenge already, ID isn't part of a request. So we need to add it somewhere. It can be, but it also can be part of final response we send back to the client. We're also sometimes it can be present, sometimes it doesn't. We not know the cost of retrieving fields. So whenever those are present, we try to use them. We'll have to be careful of type condition typically. Created that here can be retrieved from different subgraph, from post one, from videos. So there's often multiple paths to retrieve something. A post is here, there's also schema mismatch problem where here a post is an event at the supergraph level, but it isn't necessarily in the subgraph level. So I can't just send fragments directly to the subgraph. Sometimes you need to change the query. And you have the opposite situation with inaccessible, where some parts of the subgraph shouldn't be exposed at the supergraph level, and we even filter them out during runtime from the response. And this can be even more complex when you have like 40 bugs, and so validate all the incoming data, maybe too strictly from the Netflix presentation, but that's what we do. So how would you actually plan all of this? So let's redefine a bit our problem. We want a plan that retrieves all the requested fields. We want to respect the ordering of those fields as part of GraphQL Spark. And we want to minimize the number of GraphQL requests because that's the only real metric we can optimize for. We don't know the cost of fields or anything. So to resume a bit the challenges, a fit can be resolved through multiple different ways, different subgraph, different keys. A post can be identified by an ID or slug, something else. It can be a Apollo Federation, composite schema, Grafbase extension. Not all paths are equal. Sometimes you retrieve something from subgraph. You can retrieve many, many things, and sometimes you can't. And provides also can change that behavior of you can provide additional fields, additional data if you go through this specific field, which you can't in other circumstances. Requirements can be really tricky with key, but also require. They can be arbitrarily complex. You can have many fields. You can be arguments. You can have selection sets. Those your requirements can have requirements themselves. So it's really a chain that you need to take into account. And the first part, okay, surely there's a problem. This is a problem that we can transform with something that has existing solution in the literature. And obviously, GraphQL query is more or less just a tree. So let's go with it. We'll take similar queries before, just we remove a post, we keep like channel name. And this is the tree that we represent like for the query. So we have feed, created, title, channel. And so how to represent resolvers inside it? So I think, okay, we can add like a node that represents a resolver. We request something from feed subgraph, and then another thing from video subgraph. Then the question is, okay, how do we express that? Those nodes are a bit different. They have a cost. And so we'll press as like, okay, I'm adding a weight to the feed node. There's also weight to the incoming edge of a video node. So to express, okay, those aren't free. We need to take this into account. And this is actually really similar to problem mathematics. That is the directed Steiner Tree problem, where you have a root node and you want to reach a certain set of terminal nodes. And what you want to do is minimize the total weight of all the edges within the tree. So here in this example, he has multiple paths for the different terminal, but the best one is going through B and C and not taking the A path because it just adds additional weights. And so this directly translates to the previous design we had where, okay, each request has a cost. We want to minimize the number of requests. So what we do for the GraphQL gateway is that we first create a solution space. So we'll query of, okay, what's every possible way we can retrieve something. We create from this a directed Steiner tree, and we solve it. And from this solution, we have a query plan. So let's take back our example and create a solution space from it. So we have this query. Let's add first a resolver feed, because we need to resolve it some way. So we have our feed resolver, we've shown before. We have an addition box here, which is feed@feed, which is basically saying, okay, my feed field is resolved by the feed resolver. And it allows us to keep some state in the graph to see, okay, here it is resolved by this specific field. And we'll see it's useful a bit later. So next step is, okay, let's add every field we can resolve with this resolver. So here, just create that. We did a new resolver now for typically video title. So let's add a new one. We have video entity, because it's an entity retrieved from a video subgraph. Here the blue box for title at video, and we have a requirements. We don't know yet how to handle it, but we just keep it in the graph saying, okay, there's a requirement. We'll see later how to deal with it. Same thing as, again, we add like all the fields we can retrieve from the video subgraph, so channel name. And now finally we need to deal with video ID, and here it's pretty simple. We have a feed@feed, and feed subgraph can provide actually ID. So we just add the box, and here we have our solution space. So here there's slight gotcha. We do assume that composition that showed that we have a possible path, and if we don't find a solution here, nothing that could provide it, we just fail. Now I'll present like a bit simplified version of DST. We'll come back a bit later how I will actually generate it. But here's the DST for the query presented. Like we have so the different event created that, video type, channel name. We have the two resolvers. And the first question is, okay, what weight do we actually assign to those? Before we just like W1, W2. And so somewhat arbitrarily, we assign a weight of 10 to GraphQL requests. So for feed, it's pretty obvious. There's no requirements, so we just assign a weight of 10. For video entity, it's a bit more tricky because there's a video ID dependency. And so how to express that this resolver might be a lot more expensive than we know it, because maybe requirements are super expensive to retrieve. Maybe we need many resolvers and things like that to retrieve this additional data. And so what we do is, to reach video entity, we actually need to go through feed. So we can assume that this path was already taken, that it's basically free. And from this situation, how costly is it to add actual video ID? And in this situation, it's pretty easy. It's actually 0, so the total cost is 10 here in this case. And if you're really sharp, and it's actually a smaller DST within what we're trying to solve, with root being the same root, and we want to add video ID to this particular, so we want to find the shortest path basically to video ID. If there are multiple requirements, then we want basically the shortest street at least to all of them. And that's how we solve general requirements. So most cases can be optimized out like was before feed ID because it's trivially providable. But in other cases, we basically see all of the requirements that we need to have, what's the current state that we already providing, or that we know we'll already do as requests, and we see what's the cost of all of those additional requirements. And reiterate on it until basically weights don't change, because as you can have requirements depend on other requirements that depends and so on, the later will impact the cost of the former. And so back to our Steiner tree, we have so this final Steiner tree with 2 edges with weight of 10, and now it's a question, how do we solve it? And here we implement like an algorithm that is named greedy flag. We implement like a few adjustments. So how does it work? The core idea here is to think of terminals as a source of water, and it's filling the graph from the bottom up. And the edges are pipes that need a certain amount of water to be filled. So in this example, we have first the terminal that is filled with water. It will fill the 2 incoming edges from A and B, and both have weight of 1, so both will be filled at the same time. And then at the next step, we'll have the edge from A to root that will be filled, because it has the lowest weight. And we have here our solution that goes from root to the terminal, and we have found the directed Steiner tree. And we iterate on it until we have all the different solutions, because one iteration might be not enough, hence the name greedy. And so let's take this to our previous example. So it's back our a Steiner tree for a query. We have so the channel name, video title, event created that are the terminals of this tree. And we compute the requirements weight as we did before. We run the flag algorithm, first one. So we have this tree where we have video entity, the feed, everything is in part of it. We notice now that, okay, we need actually video ID. It's not optional anymore. And so we add it as a new terminal. We recompute any necessary edge weights, and we run flag again. And here's the final tree. So here it was pretty obvious because everything was included all the time. So we'll make a slightly more complex example where we have another subgraph which is named grade feed that can provide really everything at once. So obviously, since it can provide everything at once, we want to go through it. And so this is the solution space. It's more complex, and we still have the same terminals, which is like we have root, we have event created that, we have our channel name, video title. And now the question is actually, how do we build the Steiner tree from it? And what we do is that as the solving that Steiner tree is really expensive, we want to simplify it as much as possible to only keep the nodes where there's a choice to be made. And so the final Steiner tree, that what it looks like is this one, where we have, okay, we still have terminals, video ID, channel name, event created that we want to retrieve, and we roughly only keep the different nodes that have a path. So we don't have video channel because it's always retrieved the same way as channel name itself. And if we solve the greedy flag, we find out that we go through greedy feed that provides everything at once. And to our original example, this is the actual Steiner tree that we're actually solving, because as I said before, we take all the edges. Since we're taking everything, there's no choice to be made. We just skip the whole thing. We know already, okay, we need to take everything into account. There's no choice. So we can skip the whole greedy flag, weight computation, everything that can be potentially expensive. And now we need to build query plans from it. So this is what we end up after solving the DST. Every plan has a resolver. We know how to execute it. It has a set of fields to resolve. It has requirements. We keep them really at the field level. So we know that video entity depends on video ID, that nothing else depends on it. We know what each one will receive. And we need to do some additional post-processing because we lose some information in the graph. So we have to ensure that mutation fields are executed in the right order. We have to break partition cycles, and we have also to ensure that some fields, for example, when we add requirements, that they don't conflict with something existing already. So for example, title, if I rename it to ID, then I have to be sure that I don't retrieve ID I need to alias it in some way. So we did a quick benchmark on it to have an idea of how it actually performs with a use case that is one worst case scenario for query planning, where this algorithm we expected to at least perform better than what we had before. And so it's one worst case scenario. There are others. The idea here is that you have many different subgraphs, and they all expose something very similar, but not exactly the same thing. And you want to retrieve all the data from all of the subgraphs at once. And this forces basically the query planner to consider many different paths. And but there's some paths that are better than others. In some paths you can retrieve like many fields at once, others not. And so this is the results we get. So it's really small for us. We end up like only running in 20 ms for no cache. And what's interesting is also how many subgraph requests we actually end up doing. And here we only do 80 instead of 200. And so that means that we found actually a more optimal solution within that huge solution space. And now let's move forward a bit like with how we execute all of this. Typically, what I didn't mention before is that we don't treat yet skip and include and also authorization extension that can remove certain fields. What we do is actually we plan everything that might be needed, and we only change after the plan has been made. This allows to basically reuse the same cache plan, and as we keep requirements at the field level, we know what to remove. So for example, if we had an include directive on a video fragment, and we only retrieve in certain cases, then this is the query plan that we'll execute. We don't retrieve a video ID because we know we only need it if we retrieve some field from video. And the query plan itself is then expressed simply as a directed acyclic graph. So we have all different resolvers. We know their requirements, so that we get from fields, and we execute everything as soon as we can, as soon as the dependencies are resolved or perfect. We execute it as soon as possible. And for the question like, is there any N1 percent problem? No, because our resolver basically works on a list as an input. So whether it's a list of video, a matrix of video, a single input, it's always a list of video that it receives. It outputs a list. And now, one thing also with the gateway is that it's on the critical path for basically every request. So you're adding latency to everything. And so ingesting those subgraph responses can be quite costly because we're deserializing, reserializing them, we're validating, we're merging different subgraph responses. So we try to be as cheap as possible for this. So one aspect is that each of those resolver work independently from each other. So they write a different part of response, and we really minimize the data movement. So we only need to, I would say, lock, but it's not really lock, the word response part, the whole different response when we read requirements, because when we read requirements, we don't know from where exactly they will be coming from. Another aspect that we do is that to catch inaccessible fields or to catch errors and propagate null, things like that, we pre-compute the shape of everything that we will receive in advance, and that is part of a cache plan to know, okay, here from the subgraph, I expect a fit field, I expect an ID, I expect to create that, and that allows us to validate during the serialization and avoid like any intermediate allocation to avoid typically, oh, I get everything, I allocate in some generic JSON structure, and then I do my validation. Here I do everything at once. And finally, we just need to return that response back to the client. There's one thing, like we said at the beginning, we want to respect the ordering of those fields. So what we do is during the whole process, we keep track of a position of each field within the query, and we then just order the fields by this position. So in this case, even if there's retrieved from multiple different subgraphs, we know that created at must always be before title, and we will ensure that it is ordered in the same way. And this also allows us to skip any field that weren't requested. So video ID won't have any position because it's not part of our operation, and so we can just skip it. And so same thing, we did a few benchmarks to see how it performs. So here we have a 8 megabyte response, so it's really a case where you want to see how long it takes for you to deserialize a response to or manage this. So here results we in pink with high router at the bottom. Then there's efficiency. So everything is like in our repo GraphQL Federation benchmark. If we want to look more videos of what exactly we're measuring, how we're measuring, and different use cases. Here's the how efficient in terms of requests per given CPU or gigabyte. We have a similar version of this benchmark where if we have 10 clients requesting the same response, but with a national subgraph request, which that has a delay of 100 ms, that forces the gateway to keep those initial big responses for longer within the gateway to have an estimation, okay, how does Woolly behave and better measure of memory. And we have similar profile of latency, a different measure, like here should show actual memory that is being used. But we have similar behavior. And another benchmark we do also, we took it from the Hive, from the gateway benchmarks, where it's a fairly complex query with like 10 roughly subgraph requests. We send 500 requests per second without requested duplication. So here, all the gateways behave similarly, except half that is really high. We have different query efficiency graph. And lastly, we do one with requested duplication. And it's bits very similar where Hive somehow doesn't duplicate as much as it should. Maybe I missed something. And here also it's interesting to see how much subgraph requests are actually retrieving. And here, for example, we see that we do less than one subgraph request per supergraph request. And that's pretty much the end of our graph-based deep dive. So any questions?
Actually, when you make big changes to the report plan and all that, how do you go about testing and make sure that you kind of get all the edge cases out of the way?
So there are two things. One, the Guild made a great repo federation audit, which has a bunch of different edge cases, federation itself, federation spec, because there isn't really a spec, contrary to composite schemas. What we do is to test is exactly all the graph you see. I'm actually generating, it's an inside the test, inside debug logs inside, and this allows me to see, okay, what's the behavior? So we have a bunch of tests, and I still see, okay, is the graph still the same as before? And it allows me to test the different steps and to see, oh, here there's something else, here there's a requirement that doesn't exist anymore, or I did plan something different.
It's like a Grafbase format, so it's text, so you can snapshot this.
In case of these sort of cyclical queries, like when you have books that have an author has books, and then the same book may reappear or author, are these new nested nodes treated as new nodes? So this is really a tree, or is it actually like more of a graph with cycles?
So today we treat it as a tree. One of the reasons is that the tricky part with fragments is that you could query, oh, there's always exactly the same surf, so I can maybe plan it the same way. It's not always true. Maybe in some cases we want to plan it in one way, in another case we want to plan it a different way. So today we just explode over fragments and we see everything we do. And what we want to do is have a second algorithm afterwards that deduplicates everything that is similar. So everything that we would plan similarly, we deduplicate them and just say, okay, here we see the actual books we planted exactly the same way. We can just deduplicate them and have a single graph. But today we explode the whole thing. So we don't really use the knowledge, okay, this is a fragment. And this is also one case where you don't necessarily have fragments, but you might have exactly the same thing. We were trying, for example, to retrieve like user data, but at different level. So, for example, not of a person, not of a comment, or not of something else. But it's always the same thing retrieved. And so that's why we want to go through the duplication approach of basically this of a query plan. Okay, then that's pretty much it.